when you're about to leave the routine is the post condition. What needs to be true when you're leaving the routine. And you've all seen those things before. And then when we're proving proof of correctness, we want to prove that if the precondition is true and you execute the code, then the post condition will be true. And one little note, well, if the precondition is not true, then we don't have to worry about it. You know, you can be polite, but we don't care what happens. All right, so let's think about, we haven't gotten to loop invariants yet, but we're thinking about assertions in general. You know, what's the advantage of inserting assertions as you go along? Right, so here's a block of if-then-else's that we want to kind of prove that they work correctly. Right, we have an assertion at the beginning, assertion at the end, and what we want to prove is, well, if we're at the beginning and the assertion's true, then no matter what happens, however the conditions, whatever path we follow through, when we get to the bottom, the assertion at the bottom will be true. Right? And the problem with proving this is that if you have R such if-then-else's, then there are 2 to the R different paths down this, through this, right? And it's hard to check all 2 to the R of them. So what do you think we do instead? Yeah, we're going to go one step at a time. You know, we'll first say, hey, if we're up here and the condition is true, then we're going to execute this code, right? And so if the assertion's true and this condition's true and we execute this code, then we prove that this statement is true, right? And you also prove that if this is true and this is false, and you execute this code, then this assertion's true, right? So that's only 2 things to check. And then, of course, you have to do the same for each of them. So that's kind of 2 times R as opposed to 2 to the R things to check. All right, people with me there? It's pretty straightforward, but that's the game we're going to be playing. So here's an example. If this is the example we had last class, right? If we have 3 numbers and we set m to be A, then, well, m is the maximum of A, of the set containing just A, right? And if m is a set just containing A and B is greater than m, and we set m to be B, then m is the, right? Conversely, if m is the greatest of these and b is less than or equal to m and we don't do any code, then this is still true. Right? Does that kind of make sense? How you can get from here to here to here. Any questions about what we're doing? So when we're thinking about the algorithm, we're thinking about these sequence of assertions. And only later are we kind of filling in the gaps between the assertions with code. All right, so now we're going to do the same with loops. A loop invariant is an assertion that we're going to stick right here at the top of the loop. All right, and it needs to be true every time we're at the top of the loop. So here, for example, our data structure has 2 values, right? It has, and other than the array, which we're never going to touch, it has 2 values. It has the value I and the value m. And our assertion is going to be some relationship between, you know, which values of I and m are allowed, right? And this statement is going to be, well, whatever your I is and m is, it has to have the property that m is the maximum of the values between 1 and I. Right? So as I changes, m needs to change. All right, so that's our loop invariant. That's what we want to be true whenever we're at the top of the loop. So, and this is just kind of what I said a million times already. You know, when you're thinking about an algorithm, in some ways, this is the first thing to focus on. You know, it's not something that we add to the code later. You know, when we're trying to think, oh, hey, let's come up with a new algorithm for finding the maximum of a list of numbers, we want to leap in and say, hey, what do we want it to be true in the middle of the algorithm? Well, maybe what we want to be true is that we know the maximum of the first I numbers, right? And if I tell you that, in some ways, that tells you an awful lot about the algorithm, right? So how do we prove correctness? So let's look at this. This is what, when we talk about an iterative algorithm, it's going to have this sort of form. There's going to be a precondition, there's going to be a bunch of code, and then the loop invariant, at the top of the loop we'll have the loop invariant, this statement. I like putting the loop invariant before the exit condition, and some people, when you're writing code, like to do while something is true, keep going. Those are just as good as exit when, continue, all that you have to do is take the negation of the exit condition, right? But I like it in this form because it tells you not when do we continue, but it's the statement of when do we stop, right? And then you have the code that you do each iteration, you have a bunch of code to clean up at the end, and you have the post condition, right? Those are going to be the blocks that we're going to have in all of these programs. And definition of correctness is as before. If we're at the top and the precondition's true, right? Our data structure has that property, and we execute this code. Well, we want two things. One, we want to say that we eventually get here, and we also want to say that no matter what happens in between, when we get here, the post condition would be true. Right? So how do we prove that? We don't know how many times we iterate or anything, but it's going to be the same ideas that we did in the last example. We're going to kind of we're going to step from one assertion to the next. Right? So the first, we're here, this is true. We do execute this block of code, then this has to be true. Right? We're just going from one assertion to the next. So that says, if the precondition is true and you do some initial code, then you establish that the loop invariant is true. Right? And then you say, well, suppose the loop invariant is true and I don't exit. Well, that's the same as that if sort of statements before. If this is true and I don't exit, then I execute this. Then the next assertion is this again. Right? So if you're at the top of the loop and you haven't exited yet and you do a step, then when you come back up to the top of the loop, it needs to be true again. Right? And then what happens? Well, I'm at the top of the loop and I go around again. Right? Do I have to prove it a second time?
Yes.
How many times do I have to prove it? All right, so here's the joys. We don't know how many times we go around. We prove it once. We prove it once. We want to prove, and this is, if people are focused in their mind of things that aren't there. If they say, oh, I know I'm hitting it the first time. What's the second time? If it's the second time, the third time. Right? Then in their mind they have things that aren't in this picture, right? So we want to avoid thinking about things that aren't in the picture. If you want them in the picture, put them in the picture. So the way I like to say it is, we fly in from Mars. We just land here. We're Martians, right? What do we know? We landed right here. We don't know how we got here. All we know is that the loop invariant is true. Maybe we've been around a billion times. Maybe this is our first time around. We know absolutely nothing other than the loop invariant is true, right? We know that the exit condition is false, right? We know that we execute this code. We then have to prove that when we get back up here, that the loop invariant will be true again. Right? Does that make sense? And then one foul swoop, we've proved it for any number of times going around. Right? And that's back to the whole induction stuff. People good with that? All right, so then, hopefully, at some point we'll have to prove that eventually we exit, right? We'll have to worry about exiting. It's, termination at another point. But let's suppose that we've exited, right? We're down here. after the loop. And we have to think, what's true when we're after the loop? Well, one thing that's true after the loop is the loop invariant's true. The reason it's true is because we maintained it, right? We know the exit condition is true. Why? Because we exited. So from those two things, we then have to do a little extra code here, the return m, which will then give us, we then have to formally prove that these things together give us the post condition, right? And again, we can use the Martian technique. Forget everything you know. All you know is that the loop invariant is true and the exit condition is false. And from, the exit condition is true. And from those, you need to get the post condition. Right? Does that make sense? And the other advantage of thinking about it in these blocks is now you can prove the different parts in any order you want. Right? We don't have to prove that the precondition gives you the loop invariant first. You know, you could first talk about maintaining the loop invariant, or you can do these in any order that you want. All right, so this is just the partial correctness that we've talked about. Partial correctness means that if the program stops, then it gives you the right answer.
I have a question. So if the code doesn't even go into the invariant, does it mean that the invariant is true? Like it doesn't even, like it starts the loop, but the invariant is false.
You mean if the exit condition is false, or the invariant's false?
Invariance, like it's not that the invariant's false, but it doesn't. It means well, maybe like the precondition is bad or something, but.
All right. Well, if the precondition's bad, then we don't care what the algorithm does.
Okay. So do you always assume that the loop invariant is true, even if it doesn't run through the loop?
Well, you have to. We never assume it's true. We have to prove it's true. Well, I mean, you have to prove when you're going around. You assume it's true at first, and then you go around and you prove it's true.
So can it not run through the loop and still be true?
It doesn't even go into a loop.
You mean if it hits and exits the first time?
Yeah. Right.
Well, then you're never going around. You have the steps that if the precondition's true, then you make the loop. You prove that the loop invariant will be true.
Yeah, but it doesn't run through.
And then if the loop invariant's true and the exit condition's true, then you have to prove the post condition's true without going around.
Yeah, you can still do that.
Yeah.
Okay.
So it goes around 0 times. It's fine.
Okay.
Yeah, for sure. Right. So these were the 3 steps we talked about. You have to prove. You have to define the loop invariant to prove that from the precondition you can establish the loop invariant, you can maintain the loop invariant, and from the loop invariant and the exit condition you get the post condition. And from these it proves that if the program terminates, then you get the right answer. To get the termination, then we have to have this measure of progress, and every iteration you make progress, and that if you hit a certain amount of progress, then you exit. We tend to, most of the algorithms we're going to worry about, termination is less of an issue. All right, everybody kind of get what we're doing here? All right, so we're going to do a really easy example. You've all seen assertion sort before, right? And so this is just saying, you have to practice, even if you've seen it. So, you've all seen this code, and I could look at, as I've said, I hate code. I have to look at this and say, what the hell is this doing? It takes me a while to figure out. So we don't want to look at code, right? Instead, we're going to go through these steps, right? And so the first step is specifying the pre and post condition. And the precondition is we have a bunch of numbers. Maybe they're repeating, and the post condition is that you have the exact same numbers as you had before, except they're sorted, right? And we have this little picture. I always like proof by picture. Here's the input. It's a set of numbers versus here it's an ordered list, sorted list. All right. So we have to determine, come up with our loop invariant. We have to think. We jump into the middle of the computation. What do we want to be true, right? Well, it could be true that we figured out that the one number is less than this. We could figure out some weird information about our input, the third number is less than the eighth number. But that doesn't sound so useful, right? We want to, that's kind of coming up in a tree. We just don't know how to proceed when we have that weird information. So our loop invariant is going to say some of the numbers have been sorted, right? And the rest of the numbers are still on the side and we haven't looked at yet, right? So that will be our loop invariant. Everybody get that? Right? It just says you've sorted some of the numbers and the rest of the numbers you haven't looked at. Now that doesn't specify very much, right? It doesn't specify how many numbers have been sorted. It doesn't specify which numbers are sorted, right? It just says some of the numbers are sorted and the rest are not sorted. That's all our loop invariant says. So it's really a kind of, it doesn't sound all that exciting, but now we need a measure of progress, right? So what's the obvious measure of progress? Right. Well, measure of progress would say how many numbers have been sorted or how many numbers haven't been sorted, right? One's going down, one's going up. It doesn't really matter which. I officially said that you wanted the measure to go down, so that's why I said that one, but it could as well go up. All right, so now we need to find a step. We fly in from Mars. All we know is that we have some numbers sorted and some numbers not sorted, and we want to make progress while maintaining the loop invariant.
Go back to the last slide.
If I come over here, I can.
So this defining measure of progress, is this somewhere in the assertions, or is it just something mentally that we're doing in our head?
Yeah, it's not part of this. It's not part of the loop invariant. It's an extra step. You have to define a loop invariant. You have to define a measure of progress.
Okay.
And then you have to define your step, and then you have to prove that if the loop invariant is true and you take the step, then you both make progress and maintain the loop invariant. So what's the obvious step? Right? We don't want to work too hard. We don't want to think too much. We just want to do a little thing to make progress while maintaining the loop invariant. Right. We just grab some number, doesn't matter which one, and we insert it. We are doing insertion sort here, right? So that again, this step isn't being specific as to which one we grab, or it's not talking about the data structure, how we're storing these things. I didn't even say how we find where to put it. Right? But somehow we find where to put it, right? And that's our step, right? And it should be then you have to prove things. You have to prove that we've maintained the loop invariant. You have to prove that we've made progress, right? And people asked last class, well, what do your proofs look like? Well, that was kind of a proof, right? I mean, sometimes they get slightly harder than that, but not that much harder, right? And so now we have to put all the pieces together, right? At the beginning, we have our precondition, and from the precondition, you have to establish the loop invariant. Well, you want to establish the loop invariant in the absolute easiest way possible. Right? So the easiest way possible is we say, oh, look it, we have some of the numbers are sorted and the rest are not sorted, and the number we have sorted happens to be 0. Right? So it was and this often establishing the loop invariant is just this. It's a conceptual shift, but it's not, you really actually don't have to do much. Right? So that establishes the loop invariant, right? Since precondition gives you the loop invariant. And we need our measure of progress isn't too far. Well, we don't have the measure of progress is n, and it's going to keep going down by 1 each step. So, we're going to have termination. And then we keep iterating until we stop. Well, we haven't actually defined our exit condition, I don't think, but what's our exit condition? Is that we have no more numbers over here. Right? So now we have to do this step here. If the loop invariant is true and the exit condition is true, right? The loop invariant says we have some of the numbers are sorted and some of the numbers are over here not sorted. The exit condition says the number not sorted is 0, right? So that kind of gives us the post-condition is that they're all sorted.
When you say this will be our proof, does it mean we can prove just by drawing pictures?
Sometimes you might want to err on the side of safety, draw a picture and put a little English expression so we make sure you've got all your bases covered. Because I may or may not understand your picture. Right? But I do like pictures. I don't want to discourage pictures. I want to encourage the right picture. But so in fact, what I recommend if you want to cover all your bases, say it in pictures, say it in English, and say it in sort of first order logic, and you'll be sure to have it hit. Right? And if
as long as you understand, we get the mark.
And as long as I understand, exactly. As long as I'm convinced, no, it's not only as long as I understand, because I do understand. As long as I'm convinced that you understand.
So as long as we show we understand, we don't need actually a mathematical proof of these things. We just draw pictures and write English words.
Let me tell you the part of the math that I care about the most. All right? And it's sort of laid out in the steps. Suppose that we're trying to prove that you maintain the loop invariant. If we have it. Here. Right? Suppose you're trying to prove this. When in doubt, you should I want to see at least the following things in your proof. I want you to say, assume the loop invariant's true. Hence, what do we know because the loop invariant's true? Right? Assume the exit condition's not true. What do we know because of that? Sometimes that's useful, sometimes it's not. We execute this code. What does that mean? Right? And then you do a little bit of chat, right? And then you say, hence it follows that this is true. Right? So what I'm seeing there is the block of the proof is right. Right? And the only part you have to fill in really is, well, what does this mean? What does this mean? What does this mean? How do I argue that that proves that this is true? And what does that mean? Right? You know what I'm saying? I mean, because you think, maybe you're thinking, oh, well, that's obvious you do that. But, I've read lots of proofs where it's just, I don't know, I don't even see the structure of a proof there. Right? But this is the structure I want of the proof. And then, and when you fill in the parts, if you think it's a reasonable proof, I'll probably think it's a reasonable proof. If you think you're bullshitting, then I'll probably know. Right? All right. Any questions about that? All right, so now we have to do the running time. All right. So the first time when you insert the first time it maybe takes 1 time, but then when you insert the second one it takes 2 times, and then 3 times and 4 times, right? Because you have to find the place. Right. So then the total running time would be the sum of 1 plus 2 plus 3 up to n. Right? And so this is why we need to do sums. And remember that was the unit 0 is about doing sums. And so one way to think about proving what the sum is right, the area of this triangle is 1 plus 2 plus 3 up to n. Right? And well, I just take the same triangles and I flip it so that the area of this is what we want and the area of that is what we want. Right? And you put them together and what do you get? You get, this is n numbers and this is n plus 1 numbers, right? So the number of balls here is n times n plus 1. Well, half of this is what we want. Everybody kind of good with that? So, we could calculate what the exact sum is, and this one is not so hard to do. But in general, what we want to do, this chart is everything you need to know about summations is in this chart. All right? And what it's saying is, suppose we want to know the sum of f of 1 plus f of 2 plus f of 3 plus f of 4 up to f of n. Right? And suppose that f is a polynomial. Right? So let's have another. Oh, here's some more examples right here. What's 1 squared plus 2 squared plus 3 squared plus 4 squared? Right? Squared is a polynomial. Right? So more or less, in polynomials, more or less half the terms are all about the same. Right? N over 2 squared is about n squared. So the answer then will be the number of terms times the biggest term, except we're ignoring a constant in the front. Right? People kind of see that? So the technique is, I'm trying to do the sum. I see, hey, this sum is a polynomial, right? So it's the number of terms times the biggest term is the answer. And we're going to be doing more of this stuff later. So it's basically, this is all the different functions. And for all the polynomials, that's what the answer is. It's n times the biggest term, the last term. All right, so that's where we get order n squared, right? It's the number of terms, n times the last term gives you n squared, except we're ignoring a factor of 2 in this case. All right, I don't know if this is also useful, but at one point I made these pictures. It's kind of a relay race, right? Your job, this is kind of what I'm talking about. You want to focus on only one job at a time, right? You don't want to think about the entire algorithm at once. You want to think about your one job at a time, right? And so what's your job here? Right, so the first guy, his job is to get the baton onto the field, right? He needs to establish the loop invariant. And then the next guy, well, he gets the baton from the previous one, and his job is to go around again, right? And then the last guy is to come off. Everybody kind of get these steps? All right, that was just. Oh, here we just kind of, and then people say to me, oh, we want you to trace through examples, right? So we're just kind of tracing through an example of insertion sort, for whatever it's worth. All right. All right. So again, the purpose of doing this wasn't so that you learn insertion sort because you knew it already, right? But to talk about this. So I wrote this paragraph many years ago, so now what I'm wanting is the same paragraph but labeled as to the steps, right? But if I said to you, walking down the street, I said, what is insertion sort? You could say this list here, and you could see all the steps are in there. All right, so let's go through it here. Like we maintain a subset of elements that are sorted within a list. The remaining elements are off to the side somewhere. So what does that just say? It's the loop invariant, right? Initially, think of the first element in the array as being a sorted list of length 1. What did we just do there? We established the loop invariant. And we did it a slightly different way than we did by 0, but that's okay. One at a time, we take one of the elements that's off to the side and we insert it into the sorted list where it belongs. This gives a list that's one element longer than it was before. What do we just do then? We maintain the loop invariant and we made progress. Right? When the last element has been inserted, the array is completely sorted. Right? We got the post condition. Right? People gotta see that? No code involved. Right? And here, selection sort is the same basic thing. The only difference is that we maintain that we have the k smallest guys over here. Right? So it's a slightly stronger loop invariant. And then the step is you look over here for the smallest guy and you put it on the end. right? For selection sort. People kind of got that? Everybody good here? All right. So now we're going to do back to propaganda. You know, a lot of what I do here is propaganda. Think about this as a political science course, right? So we need propaganda, right? So how do you come up with an algorithm, right? You have to design your own algorithm, and it's hard to come up with new algorithms, right? I mean, that's why we want to get paid the big bucks, right? So the one thing I've been emphasizing is thinking about it as an algorithm as a sequence of assertions as opposed to a sequence of actions. And the key assertion is the loop invariant, and the loop invariant is hard to come up with. It's part of the art. And when I started teaching this, you know, people ask, well, how do you come up with a loop invariant? And I had a hard time knowing how to do that other than examples. But we'll see in a few minutes. I think it's in a few minutes. We'll come up with, I've broken it down to different types of loop invariants, so it makes it easier. Right, but once you have the loop invariant, often the rest of the algorithm is follows. And this is what I've said before, you know, the loop invariant is key. Come up with it first, not as an afterthought. Don't start coding. Right, you can start. If you're coming up with a new algorithm, start with a small input and see, hey, what would you do to solve this input? You know, and then you start taking steps. So I'll do this action and then you want to say, you want to think about your loop invariant. What's going to be true? What properties do you want to maintain as you do these steps? You know, and I like thinking about it is, again, the sort of the Mars thing. I want to solve this problem. Let's just leap into the middle of the computation, right? What do I want my data structure to look like at the middle of the computation, right? We don't want to start with what do you do first or what do you do at the end to clean up. We want to start with right in the middle, right? Let's draw a picture. Let's write some mathematical statements. That's, you know, an English statement to say what do you want to be true in the middle. Right? You know, we have some numbers sorted and the rest of the numbers are onto the side. Right? That's a picture of what you want things to look like in the middle. Right? And in some ways the loop invariant, you know, this slide makes me nervous, but I know other people talk about, you know, this kind of combines the idea of the measure of progress in with the loop invariant, is that somehow the loop invariant kind of points out, you know, what's been done versus what's yet to be done. And the other thing about the loop invariant is it wants to be taking small steps, right? It breaks up the entire computation into, well, there's this state, the loop invariant here, and then the next loop invariant, and the next, right? It breaks the computation into little increments, little steps that flows naturally from the precondition to the postcondition. Right? If you don't know what I mean by that, think about the example of insertion sort. Right? I say some numbers are sorted and the rest are on the side. Right? Well, if the number sorted is 0, then I'm over here. And if the number sorted is all of them, then I'm over here. And there's this nice flow in between. Right? That's kind of what we mean, what we need here. All right, so I also like to bring morality and ways of living into this course as much as possible. And one thing that I believe in is that you're never going to get what you want in life if you don't ask. Right? If you want something, you should ask for it. Now, that doesn't mean you should expect to get it. You know, if you want an A, you could come up to me and say, hey, you know, I really want an A. And that won't mean I'll give it to you. Right? But then it opens up a dialogue and we can start having a discussion and maybe we can work out a win-win in which you get what you want and I get what I want. Right? So, and what does it mean in this case? Is I like to jump into the middle of the computation and think, what would I like to be true? Right? What I would like to be true is I want some numbers sorted and the rest on the side. That's what I would like. You know, don't worry about how you're going to get it right now. Just ask for what you want. Right? And then pretend that the fairy godmother has come in and has granted your wish. You've leaped into the middle of the algorithm. You have some numbers sorted and some are on the side somehow, right? And that's great. But now your job is, from there you have to think about how you're going to maintain it, right? The fairy godmother's given you the loop invariant, and now from here you think, okay, great. Well, my job now is to just make a little bit of progress while maintaining that loop invariant, right? Does that make sense? Now, if you can maintain the loop invariant while making progress, then that's exactly the goal here, but sometimes you can't. And the reason, weirdly enough, is sometimes it's because your loop invariant's too weak, and sometimes it's because it's too strong. If you don't ask for enough from the fairy godmother, then you don't have enough, you don't know enough in order to guarantee that you can make progress and maintain the loop invariant. On the other hand, if you ask for miracles, then you'll never be able to establish it initially and you'll never be able to maintain it, right? So it's a balance of being able to ask just the right things. And that's why the loop invariant is the hard thing to come up with. All right, so this is, I've said this already. You know, another thing that I'm looking for when I'm reading your proofs is that you don't assume things that you haven't stated in your loop invariant, right? You know, I've said already, you know, what I'm going to be looking for is being convinced that you get the meta steps right. Right? I mean, in the details of the proof, it would be great if they were all right too, but even more important is that you get the meta step right. So the meta step says, you know, only thing I know is that the loop invariant is true and that the X condition is not true. And then I get to do a little code, and from that I want to get the loop invariant. Right? Don't bring in anything else. Right? That's all you know. You know what I'm saying? All right, so on exams I've said, what is the loop invariant? People have given me code, and people have given me preconditions, and people have given me postconditions, and people have given me statements which are true but not all that useful. People give you, steps of the algorithm, right? These are all wrong. And you know what marks will get for these? 0. Right? Another thing that's important is differentiating between one iteration and the next. Right? Remember, you're at the top of the loop invariant's true. Right? So all the variables have certain values. And then you want to come around, well, you have new values. You want to differentiate between them. Right? So, in fact, my father is a mathematician, and when I was starting off, it was a long time ago, and he hated computer science. He hated things like this. He said, well, that does not make any sense whatsoever unless you're working base 2. Right? It's not a mathematical statement. And so you want to differentiate. You want to say, hey, well, let x prime or xi be the value at the beginning of the iteration. And hence, because the loop invariant is true, the property of the loop invariant's property is true about these. Right? And let x double prime or xi plus 1, give it a name, be the values after they come around. Right? And because the code executes, we have a relationship between them. Right? So now we know the loop invariant is true about these. We know the values of these guys from the code. Right? And then we have to prove that the loop invariant is true about these guys. Right? Does that make sense? Everybody with me? Is anybody falling asleep? I could throw chalk at you. I know, it's so hard to keep awake. I'm with you. Just be grateful that it's not a 3-hour class. Anybody, do you have any questions? Sometimes it's hard to keep awake when you kind of lose what we're talking about.
So if that was code, then you would turn x into another variable? Is that what you mean? Or is it just this is the code. Yeah.
And I just wanted this, so this is a variable, x is a variable. X prime is a particular value of the variable when I'm at the top of the loop.
Okay.
And x double prime is the value of that variable after I've come around again.
Okay.
And the relationship between their values is this. And by assumption, we know the loop invariant is true about these ones. And we want to prove that it's true about these ones.
Okay.
All right, so this was actually on a midterm at some point. And what I wanted to do is I came up with a piece of code that breaks as many of the rules as possible. And we want to see, I asked, okay, you're the marker, tell me which rules have been broken. All right? So, precondition, postcondition, right? Is this, the input is an integer I, and we want to sum up from 1, 2, 3, 4 up into capital I, right? So is that a reasonable pre and postcondition? Well, people often argue, well, what happens? You might want to add that I has to be positive, right? And I'm like, well, actually, what's the sum of 1 plus 2 plus 3 up until -5?
It doesn't run.
Hmm?
It doesn't even.
How many terms do we have? We're adding up 0 things, right? And what's the sum of 0 things? 0. Yeah, so it's okay. If you want to stick in there that I is positive, that's okay. All right, so some people argued, well, your variables need to be documented, right? And yeah, I'm always a believer in documenting your code, but have we documented our variables?
Oh yeah.
Where?
The code itself. Or no.
Well, this doesn't document it really, and this doesn't document it. What does document the meanings of the variables? The loop invariant. To me, the loop invariant tells you what these variables are and what they're doing. Right? All right. What about our loop invariant? What's wrong? Is anything wrong with our loop invariant? One thing I haven't really stressed so far is that loop invariant is a state, right? It's a picture. It's not. Description's good. Description's a state. It's a picture. What is it not? It's not an action, right? Each iteration adds the next term. What does that sound like? Sounds like an action, right? So if I'm asking you the loop invariant, I'll tell you what I'm looking for. Is it an action or is it a statement? And this to me looks like an action. It's not a snapshot, right? So let's get rid of this bit. All right, that's what it says. This documents, right? What's wrong here? We don't want an action. So let's get rid of that part.
You have 5 minutes.
I have 5 minutes. Excellent. We'll be able to finish this example. Thanks for letting me know. All right, so here, this is a loop invariant. Is it a good loop invariant? Right, we got the relationship between I and S that needs to be maintained. Right? Everybody kind of got that? Right, it's the sum of 1 plus 2 plus 3 up to little I adds up to S. It seems like a really good loop invariant. Right? All right, and can we maintain this? Everybody look, does this code maintain this loop invariant? I got some nods of yes. Let me give you a hint. Everything's wrong with this code. All right, so let's go through it. Right? Right, let's be careful of the values beginning and ending, right? Let S prime and I prime be the values when we're at the top of the loop, and S double prime and I double prime be the values after we come around again, right? So from the loop invariant, we know this, right? That's what our statement is when we're at the top. This is what's true when we're at the top by the loop invariant. Then our code adds I prime to S, right? And increments I prime, right? Then do we get our loop invariant together? Well, if you note here, I prime has been added already. We don't want to add I prime again. Right? If you look at here, we have the sum up to I. So we don't want to be adding in I again. What do we want to be adding? I plus 1. Right? Does that make sense? And that's how, we can correct little mistakes like that. People see this example?
What's a prime? Is that a derivative of I? Because it doesn't make sense.
No, it's not a derivative. It's just let's go back a line. It's what I was saying in the previous slides. Right? We want to differentiate between the values at the top and the values coming around again. Right? So we want to call the value of S when we're at the top something. And we could call it Bob, but that might not be as useful. So I just give it this name. This is just the name for the value when we're at the top. Right? And this is the name for the value when we've come around again. Does that make sense? It's not a derivative. It's just, we could call it Si and Si plus 1. We could call it Bob and Charlie. Does that make sense?
It's a changed value.
What?
It's a changed value.
Changed value?
Yeah.
Well, yeah, this is the value and it changes to this value. Right, so over here we have S prime, from the loop invariant, we know this relationship between I prime and S prime. Right, and from the code, we know the relationship between the previous values and the next values. And then we try to prove that we have the loop invariant for the next guys, and we can't because we're adding in the wrong thing. Right? Are we out of time? All right, we can finish this example next time, but it's more of the kind of same tricks. In fact, what's funny about this code is that it actually works. Everything is wrong except if we just change the loop invariant to, I don't know, sum up to I minus 1 here, then it'll work perfectly. So have a great weekend. Keep working on the assignments.